Good morning. Let's get started here. Want to mention that there are going to be two speakers coming to the class on July 27th, Monday. Peter Layton, I think he was a partner at Goldman Sachs before, and he's a very innovative guy. He will be here. And on July 27th, July 29th, Wednesday, Maxine Hardy, who is heading the linear quantitative research group at JP Morgan Chase, will be here. Okay. I'm also trying to get one other speaker from BlackRock who came last year. I think he's trying to work out his schedule yet, so I don't know when he will be able to come. Okay. I also want to mention that I think the last week of classes I won't be here. I'm going to be in a conference. So I would like to reschedule some of those two classes. Maybe those 2 weeks I'll try to squeeze in 2 more classes, So just want to alert you. I think so far, we have started on learning some tools. My goal is to finish up all the tools this week and start on, technical rules next week. That's my goal, okay? And as far as the tools are concerned, I think we started looking at modeling the average of a time series. Today I will talk about modeling the variance of the time series. Okay, and then after that I think I want to introduce the high frequency data, and the raw data comes in the high frequency form, and then what we do is to process the data into low frequency so that we can use standard time series methods. Okay. And sometimes the high frequency data, I think because of so much noise in the data, it's very difficult to see the signal. So the processing the data so that we can put them in some discrete time intervals, I think works out nicely in the long run. Okay. So I think on Wednesday I will also cover multiple time series modeling. And the reason I want to do that is that when we look at stocks, we are going to look at multiple stocks together, okay? Especially in the context of pairs trading, we are going to look at 2 stocks. That concept can be extended to many stocks, okay? So I'll also do a little bit of multiple time series modeling. And as far as multiple time series modeling is concerned, if you know how to do regression, you should also know how to do multivariate regression. And if you know how to do multivariate regression, you should know how to do multivariate autoregression. That's where I'm going to take you, okay? So before I get started on the lecture, do you have any questions? Any questions? Have you started on the assignment? Okay. If you have any questions, just let me know. Assignments is posted. I think you should be able to work on them, And if there are any questions, let me know. I think Leo or me or Licky should be able to answer some of those questions. Okay. So we talked about modeling the mean of the time series data. Okay. The reason why we want to see that is that, as I mentioned, prices generally tend to follow random walk. It may not have a single mean because the time varies, the mean also changes. But the most of the decisions you are going to make is going to be based upon the most recent data, right? The most recent data almost always have mean. You can say roughly stationary, okay? So you should still be able to use the concepts we are going to learn here, okay? So we talked about 2 ways to model. One is modeling through autoregressive process. The other one is modeling through moving average process, okay? And the difference between the 2 is not that great because whatever model you can write it in the autoregressive form, you should be able to write it in the moving average form, vice versa. You can do both, okay? The main difference is that one may give you more parsimonious representation. Other one, if you start writing, say if you have an AR1 process, if you write it as a moving average process, it may turn out to be infinite moving average. You may have to use so many terms to account for simple AR1 process. Okay, so this is the difference between the 2 lies mostly in the form of parsimonious modeling. Okay, so So the way I want you to think about these things is that after you model the data, you compute the residual terms and you calculate simple autocorrelation function on the residuals, and if you don't see any information, maybe at that point you can stop. Okay. So the modeling always has to start with some tentative models, fit the models, compute the residuals. On the residuals, do the diagnostics like computing autocorrelation function. At that point, if you don't see any information, you can stop. So that is the approach we are going to take. Okay. So here I mentioned that you could use the moving average process. So any series can be written as an infinite moving average process. The first part of it here, you can see the very top line is called Wold theorem. It's a very famous result. It says that any time series can be written as the infinite combination of error terms. Okay, but that doesn't really help you in practice because you can't have infinite series, you have a finite series. So you need to fit a finite moving average model. That model is given there. The main part of it is that finite moving average series is always going to be a stationary series, and you can show that the autocorrelation function is 0 for h greater than q. That means that when you plot the autocorrelation function, if it cuts off after a certain lag, you can decide that how many terms you want to include in the moving average term. Okay. And the autoregressive model, as I mentioned before, it depends upon p previous lags, and in order to see how many lags you want to include, you want to go for what we call as partial autocorrelation function. Okay. I want you to understand these two concepts because if you know how to use these two concepts, it comes very handy not only in modeling the mean, it also comes handy in modeling the variance too. So arch and gorge models we are going to introduce pretty much a similar concept. Okay. Because of variance has to be positive, there's some constraints that are imposed on the coefficients that come into play. Conceptually they are the same. Okay. So you use the PA partial autocorrelation function to identify AR process lags. I just want to briefly mention what exactly is the partial autocorrelation function. So in the context of AR2 model, essentially it comes as follows. Okay. Suppose you have yt is equal to pi 1 yt minus 1 plus pi 2 yt minus 2 plus at. So that is a AR2 model. Okay. And how do you distinguish between AR2 model and AR1 model? So in AR1 model you are not going to have the second term. So how do you know that you don't need the second term? One way to do this is to fit this model and see the significance of this coefficient pi 2. At that point you can decide whether you want to keep it or drop it. Okay. Alternatively, I think you can use this partial autocorrelation function, which pretty much does the same thing, right? But it does it for you beforehand so that you can take a look at it and decide how many lags you want to include, right? That's a question. So what exactly is the partial autocorrelation function? I think the way it works is that it looks at regress yt on yt minus 1. I'm just going to loosely say that regress because when it comes to time series, there are some constraints that are imposed. We'll talk about it later. Simple idea is that regress yt on yt minus 1, compute the residuals. Okay. So I'm going to call it as residual 1. Okay. And then the second part of it is that regress yt minus 2 on yt minus 1 and compute the residuals 2. So essentially what we are doing is taking the effect of yt minus 1 from both yt and yt minus 2 Then you look at the correlation between residual 1 and residual 2. 1 and residuals 2. So if this correlation is 0, that would automatically say that you don't need the second term to be in the model. Okay. So all these things are already computed for you, so you don't have to fit this model and decide whether you want to include this model or not. Okay. That's a key. Okay. Couple of things I want to mention here, because we'll come back and revisit this again. So if you have an AR1 model, what is the constraint on this coefficient here? This one is supposed to be in absolute value less than 1. Okay. So if you have an AR2 model, what is the constraints on these coefficients pi 1 and pi 2? What is the constraint? Because if this in the AR1 model, if you had this pi 1 to be larger than 1, the series will blow up very quickly. It becomes non-stationary, right? But in the case of AR2 model, what is the condition? Yeah. So the condition is that you could write this as a polynomial. So I'm going to write it here as lambda squared minus pi 1 lambda minus pi 2. Roots of this equation should be less than or equal to 1. Roots of this is less than 1. Okay, that's a condition we impose. Okay. So this comes very handy. You'll see that how this gets used later on. But I think you can see that for ARP, you have to get you'll get a pth degree polynomial. You should solve for it. Okay. Even here you can see that when you solve a quadratic equation, it's possible that both roots are complex, right? And they could be same roots, or both roots could be different, right? So you can there are all kinds of conditions that come depending upon what kind of root you get. You can show that the series is composed of two series that you add up. Okay. But this properties of this we are not going to see very heavily here. In financial time series, the main thing we are going to look for is that whether the process is stationary or non-stationary. And usually the maximum lag we are going to include is 2 when it comes to financial time series. Okay, for other macro series, macroeconomic series, you can fit various kinds of autoregressive models. In financial time series, there is no variation, so you can be done with the AR2 process. Okay. So as far as this class is concerned, if you can follow through at the modes, I think MA2 and AR2, I think that's fairly sufficient for analyzing financial time series data. Okay. Okay. So we talked about how do you bring all of them together. I think I want to briefly mention that the random walk model we talked about is going to be ARIMA 0, 1, 0. That means that once you difference the series, there is nothing much left. Okay. And the second part of it, this might be useful to know. This is exponential weighted average. I am going to write it as ARIMA 0, 1, 1. Okay. Does anyone know how to see the connection between exponential weighted average and ARIMA models? Okay. So briefly, let me write here. I think that model comes very handy in practice. And again, that model is valid only for stationary series. If you have a non-stationary series, you may get all kinds of numbers that doesn't make sense. Okay. So let me write the exponential weighted average, EWA. What exactly is the exponential weighted average? You give more importance to recent data, right? As you go further, it's going to get less and less importance, right? That's the idea here. So when you write it as a ARIMA 0, 1, 1, essentially what it means is that you're going to write YT and you're differencing it once, 1 minus B, and then it's a moving average process. I'm going to write it as 1 minus theta b times 80. Right? That's ARMA 0, 1, 1. Okay? You're differencing the series once, and then you are taking the moving average term here. Okay? So this essentially means that you could write AT as 1 minus b over 1 minus theta b times yt. Right? Just flip this around, and you can see that this is going to be, let's say, 1 minus b, and 1 over 1 minus theta b, I'm going to write it as, assuming that the theta is less than 1, I'm going to write it as theta b plus theta squared b squared, etc., times yt. Okay. Right? Because 1 over 1 minus theta b, I can expand in that form. So when I do this term here, you can see, I'm just going to do a little bit of calculations here. This is going to be 1 plus theta b plus theta squared b squared, etc. I'm going to take this minus b and write it here, minus b plus minus theta b squared, and so on. Okay. Sorry, this should be minus theta b squared, and so on. So this times yt, and you can show that this is, you could write it as 1 plus theta minus 1 b plus, if I take theta outside, theta b squared outside, you can show that this is going to be theta minus 1 b squared, etc., times yt. Right? So you can see that this is going to be, writing this as yt plus, just multiplying this, theta minus 1 times b times yt is the backshift operator. It's going to be yt minus 1, theta times theta minus 1, b squared is yt minus 2, etc. Okay. So from here you can see that it's a weighted average, because what is the condition on AT? AT is supposed to be normally distributed with mean 0. On the average it's going to be 0, right? So I can as well put on the left hand side 0 and move these terms around. This is going to be yt is equal to 1 minus theta times yt minus 1, and then 1 minus theta times yt minus 2 plus 1 minus theta times theta squared times yt minus 3, and so on. Right. Okay. Can you see that this is the weighted moving average that you get? Okay. So by fitting exponentially, by fitting ARMA 0, 1, 1 model, you should be able to estimate what should be the smoothing constant that should go in here. Okay. So I think this gives you a model perspective, because if you are not happy with the exponential weighted average, if you want to include other terms, it gives an option to think about how to add other terms into the model. Okay. So this comes very handy, because when we talk about trading strategies, one of the key concepts we are going to use is the exponential weighted average. Okay. And you can see this, all these things work only when theta is supposed to be less than 1. Otherwise you can't expand this way. Okay. So this kind of connection is valid only if you have stationary series. Keep that in mind. If it's non-stationary series, these things will blow up very quickly. You may get a number theta which is larger than 1. Some of these things can get really nasty if it get numbers greater than 1. Okay. Okay. And as far as I think this financial time series are concerned, I think if you can study the properties of these things, ARMA 010, 011 and these 4 series, that is more than enough for looking at the financial time series. Okay. So generally I think, when it comes to model building, we are going to see 2 criteria here: conditional likelihood versus maximum likelihood. Okay. And the main difference between conditional likelihood and maximum likelihood is that, how do you write down the likelihood function? Okay. Just to give you a simple idea, it's not, especially in financial time series, it's not worth wasting time looking at the difference, mainly because of the following reason. Okay. So let me briefly give you that information. Suppose I have yt, just a simple AR1 process, yt minus 1 plus at. So that is the model that you have. So you can write down the likelihood function for this. The key part of it is that what is the distribution you are assuming on at. Just for convenience, let's assume that this follows normal distribution. If that is the case, you can pretty much write down the equation for yt. So y2 is equal to, you can see, pi times y1 plus a2. So you can write down the likelihood for y2, which is given as y2 given y1 should follow normal distribution with mean pi y1 and variance is sigma square. Right? You can write down the likelihood. This is given y1, right? So what is the model for y1? What is the model for y1? There is nothing before that, right? So we cannot include any information here. Okay. So the difference between conditional likelihood and maximum likelihood is that how much fuss you want to make about this y1. Okay, initial point. Okay. You can assume some distribution, include it in the model and go through the calculation. But if you have a long series, what difference does it make to know the first observation? Doesn't make too much difference, right? So I won't worry too much about conditional likelihood and maximum likelihood. I'll just go with conditional likelihood. That's good enough. Okay. So there are 2 criteria we are going to use, AIC and BIC criteria. And how many of you have used it before, AIC and BIC? Okay. What's the main idea behind these 2 criteria? Okay. The main idea is fairly simple. I think, if you are going to maximize a likelihood function, the estimates you are going to get always going to be optimal, right? And you can always maximize the likelihood by increasing the dimension of the model. You can increase as many parameters as you want. The model fit would be very good, but model validation may not be all that good. Okay. So what this does is sort of penalize for the number of parameters you are likely to include in the model. Okay. So I would suggest that you should follow this criteria as much as you can. Although I put here P and Q. P is the order of the AR process, Q is the order of MA process. But the concept goes beyond this. You can just say that R is the number of parameters. I could have as well written this as AIC R, BIC R. So the main idea, I think, is that by increasing the number of parameters, you're always going to make these quantities smaller, but that is not the issue. The issue is that at what cost you are making it smaller. So R is supposed to be the number of parameters that sort of penalizes the likelihood function. So the idea, I think, is that, if you increase the number of parameters, you can always reduce the likelihood function, but that comes with a cost. It sort of gives you the penalty factor. The second factor in those 2 equations are penalty factors. So you should always consider them, because that way you don't engage in overfitting the model. Okay. So some of these things we saw before. Okay. Do returns follow Gaussian distribution? I think we have talked about it. We have shown that returns do not follow Gaussian distribution. And one quick check people use is this Jark-Barra test. Okay. So essentially what it says is that you look at the skewness measure, you looked at the kurtosis measure, you can compute this Jark-Barra test. Let me briefly give you one line here that might be useful. Okay. So generally I think let's assume that the returns are calculated as log of pt. I just want to be consistent with the notation here. P of t minus P of t minus 1, which I think I mentioned as log of P of t minus log of P of t minus 1. Okay. So once you have this returns here, you can calculate the average return R bar, and you can also calculate the variance of the return. So write it as the standard deviation of the return. Okay. Once you have those quantities, you can compute this skewness measure. So call it as S. So this is given as 1 over T S to the power 3, T ranging from 1 to capital T, RT minus R bar to the power 3. Usually R bar tend to be very close to 0. Okay. And kurtosis measure is given as K, which is 1 over T S to the power 4, 1 to capital T, RT minus R bar to the power 4. Okay. So generally you should expect skewness to be 0 if you have a normal distribution. In fact, you can show that S is supposed to follow normal distribution with mean 0, and standard deviation is given as square root of 6 over T, and kurtosis is supposed to follow normal distribution with mean 3, and standard deviation is given as 24 over T. Okay, these are all large sample results. Okay. And for that reason, I think we are going to say that since you have a normal distribution here, you can construct a standard normal distribution out of this. S divided by square root of 6 over T squared. This is supposed to be the quantity inside the bracket is supposed to be normal 0, 1. So if you square it, you get chi square 1 plus, from there you will get k minus 3 over square root of 24 over T square. Since you have this chi square 1, assuming that they are independent, they are taken to follow chi square 2. This is the Jark-Barra test. Again, this is a sort of a, I mentioned that somewhere, I think it's an omnibus test because it combines both deviation from skewness and the deviation from kurtosis. It combines them together. It's possible in some cases you may have skewness violated but not kurtosis, the other way around. So this is just a quick way to check if any one of them has been violated or not. Okay. So What happens if there is a violation of this? Okay, what exactly is going to go wrong when you make inference? The inference is going to go wrong only in the tail distributions. Okay, so there are a couple of alternatives people have looked at. There are so many other distributions that are in the place. I think the commonly used alternative is this log normal distribution. Okay, so what is the property of log normal distribution? Generally, you can show that log normal distribution is slightly skewed to the right, so it sort of represents the true nature of the returns distribution. Some people tend to use it more than others. Okay, so let me briefly give you that information. Okay. So there are 2-3 distributions I've used in practice. I have a little bit of experience with them. One is this log normal distribution. Log normal distribution. Okay. So essentially the log normal distribution is that if Z follows normal distribution with mean mu, variance sigma squared, x is equal to e to the power z, it's supposed to follow log normal distribution with mean mu and variance sigma squared. Okay. So the main property of this is that median m is equal to e to the power mu. Okay. Average value of x you can show is equal to e to the power mu plus sigma squared over 2. Okay. So from the definition here you can see that average value of x generally tends to be greater than median because x is right skewed. Right skewed. So in some practical cases you can see that this right skewness tends to happen in stock data, so people tend to use this log normal distribution. There are two other distributions that I want to briefly mention here. One is the t distribution. That's another alternative people look at. The other one is the mixed distribution. Mixed distribution. Okay. So what is the difference between the two? What does t distribution do? What does the mixed distribution do? What is the main difference between t distribution and normal distribution? T distribution has thicker tails, right? So in that sense, I think it's could represent the data better. What is the mixed distribution? Mixed distribution is that we assume that most of the data comes from normal distribution, but there is some possibility that the other data can come from other distribution, right? So we can't distinguish them just by looking at the data. You can't anticipate them, but you can distinguish them by looking at the data when you plot the data. Okay, so roughly I think just to give you an idea here, I want to give you one example here. Okay, so the mixed distribution is going to be z is equal to p of x plus 1 minus p times y. Essentially we are saying that z can come from, some proportion of it comes from x and some proportion of it comes from y. Okay. Suppose I say that x follows normal distribution with mean 0, variance sigma squared, whereas y follows normal distribution with mean 0, variance is k times sigma squared, where k is greater than 1. So essentially what we are saying is that it's possible that some observations can come from a distribution with higher variance, right? K greater than 1. Okay. So obviously I think the tail probabilities are important. Okay. So if for instance if you have purely normal distribution, you can show that probability that x greater than x, this is you are looking at greater than x and less than minus x, this is given as 2 times 1 minus pi f x over sigma. Okay, where pi is the CDF of the normal distribution. Pi is the CDF of normal. So we can use the normal distribution tables to evaluate this. Okay. So you can show that if you are going to get not from x but you are getting data from z, then the following things are true. So I'm just going to briefly mention the following. Okay. For z, tail probabilities are much higher. Tail probabilities are much higher. Much higher. Okay. So just to give you an illustration here, I'm going to write the following here. So you can show that the fourth moment of this z to the power 4 is going to be 3 times p sigma to the power 4, because I'm just using this p times the fourth moment of this sigma to the power 4 plus 1 minus p times k sigma to the power 4. So by taking these terms here, 3 sigma to the power 4 is going to be p plus 1 minus p times k. Okay. When k is 1, that means that both of them come from the same distribution. You don't have to worry about it, but we know that some observations could come from different distributions. So you can see that from here this is going to be greater than 3 times sigma to the power 4. Okay. So what does the fourth moment measure? Fourth moment actually measures the curtices of the data, right? That's the fourth moment. So essentially there is a likelihood of getting higher values because some observations can come from other observations. Okay. And the property, I think, how do you estimate p? I think you really have to look at the data, where they come from, where they are located. Based on that, you should estimate the proportion that comes from there. Okay. Although I think these are all fairly well established facts, I think it's also very hard to use in practice because of you don't know the value of p, you have to estimate it, right? Then you don't know the value of k, you have to estimate. There's lots of issues here. Okay, there are other alternatives people talk about, and I think one of them is the stable distribution by Mandelbrot and Farmer. I think these are all very nice to study, but analytically it's very difficult to keep track of them. Okay. So I think couple of things before we get to modeling the variance. Okay, we already talked about why log of pt is a random walk. I think as someone pointed out that the very first paper on this came in year 1900. Louis Baker's thesis was on random walk models. Okay, I think very important thing. And then I think there are two other important developments in finance. One is the Markowitz portfolio theorem, which talks about risk and return trade-off, which is, I think, is a still fundamental rule that people follow. And then there is also capital asset pricing models by Sharp, Lintner, Mosin and Black. I think there are different versions of it. So in this particular course, I think I'm going to cover only Sharp Lintner model. I do some work in Black CAPM, but I don't know whether we'll have time to do that. So why do I do all those things? I think there is a set of tools we are going to use in technical analysis called fair value model. Okay, the fair value model essentially is asking for whether the return on the asset is fair after adjusting for the riskiness of the asset. Okay, so those riskiness are measured by capital asset pricing models, and there are a couple of ways you can do them. So okay. So are asset prices predictable? I think we'll see that when you look at the cross-sectional data, asset prices tend to be predictable. When you look at the time series data, I think the best prediction is based upon random walk model. Okay. Okay. So a few ideas, I think martingale and random walk. I think for this particular course, I think I would not worry about it. But I want to make a comment here. Okay. I think there is a belief that usual tests that we have, like testing for the unit root test, may not be adequate. Okay, and they don't see any obvious relationship between serial correlation and expected profits, and simple linear relationships are too much unsophisticated. This is a paper by Fama and Bloom, which I will refer back to it. So the main idea here is that simple relationships are good to know, but in order to implement them in practice, you need to go beyond them. It's not going to be simple. Okay, so that was the main point of this exercise. Okay. Okay. So ARIMA models focus on the mean. They assume that the error variance is constant. Variance also shifts over time. Okay. How do you measure variance? In finance, variance is a measure of volatility and okay. How many of you have done options? In options pricing, one of the key quantity is to look at how the stock price is going to vary over time. Okay, so what they call implied volatility comes a very important factor. Okay, so estimating volatility and predicting what the volatility is going to be into the future has become one of the important studies in the last 20 years. Okay, so I'm going to give you my take on it, because even after so many years, volatility models are not that good yet. There is always the big gap between what you observe and what you predict. That's a okay. Okay. So the first model, I think, an interesting model was given by Engel and Granger, who won the Nobel Prize. So they're similar to AR process. Okay. So let me briefly motivate this, and then I will talk about the important properties of this autoregressive conditional heterocadastic model. I may already have this one here. Sorry. So if you look at this written data, we mentioned that if the model is going to be P of t is equal to P of t minus 1 plus R of t. R of t, the assumption is that returns follow some distribution. Just for illustration, I'm going to assume sigma squared. Okay. So an alternative way to write this same thing is to state that RT is equal to sigma times epsilon t, where epsilon t follows normal 0, 1. Okay. So far I think we have assumed that this standard deviation is pretty much independent of the time where you are. Okay, that's the assumption we made. Now we are going to say that the standard deviation also depends on the time where you are. So we are going to extend this to RT is equal to sigma t times epsilon t, and we want to model this sigma t. Can you see that? That's a difference between what we have done so far, what we are going to do now. Okay. So what exactly are the models? Okay. So if you look at it, you'll see in this equation, let's for the time being, I think I should have put the notation, just call ZT as written RT. In that equation, what is observable, what is not observable? If I have, let's go back here. RT is sigma t times epsilon t. Which quantities are observable, which are quantities that you make up? Only quantity you know is the written RT, right? The rest are all made up. Okay. So how you make up is important, because the second line talks about sigma t squared is a function of z of t minus I squared. Okay. So if you look at this model here, does it look like a model that you have seen before? What kind of model is that? Okay. What kind of model is that? The only quantity you know in that model is ZT, right? The rest are all made up numbers. Okay. Right. So we are saying that variance depends on the past Q values, and because the variance is a positive quantity, we are going to write it as sigma t squared is equal to alpha 0 plus Q lag values of the past values. We are going to assume this alpha is positive. Okay. So just to make it easier for you to follow this, I am going to take a arch 1 model and write it in the format so that you can see how this is all related to the autoregressive and model that we have seen in the before. You can find it. Arch model. Okay. So I'm going to start with simple model. Q is equal to 1. Q is equal to 1. Okay. Q is equal to 1 would mean that sigma t squared is equal to alpha 0 plus alpha 1 z of t minus 1 square. Okay. So this is what we call it as arch 1. Okay. So in order to see how this come about, I am going to ask you to write in the following form. I am going to write it as zt squared. I am going to write it as zt squared is equal to sigma t squared plus zt squared minus sigma t squared. just add and subtract sigma t squared. Okay. So I'm going to substitute what sigma t squared actually means in the first part of it here. This is going to be alpha 0 plus alpha 1 z of t minus 1 squared plus zt squared minus sigma t squared. You can see that zt is sigma t epsilon t. So zt squared is going to be sigma t squared epsilon t squared. So this quantity is going to be sigma t squared epsilon t squared minus 1. Okay. Just for sake of simplification, we are going to write it as alpha 1 z of t minus 1 squared plus this quantity we are going to call it as error term sigma t. Okay. So what kind of model we have here? What is this model? What is that model? It's essentially AR1 model, right, in ZT square. Okay. So arch models can be written as autoregressive model of order Q. Okay. Except that we need to impose some conditions on these alphas, because you can't have alphas to be negative, because if they turn out to be negative, left hand side will not work out. So you need to impose some constraint. But generally the logic here is that you can show that this is sort of a autoregressive type of model. And one of the conditions that it's given here is that all the alpha should be positive. And I think I didn't write it there. The condition for stationarity is that alpha 1, alpha 2, etc. up to alpha q should be less than 1. Okay. This is the stationarity condition. Equal to 1. Okay. So this is the arch model. Okay. I think I make the assumption that in all these things we make the assumption that epsilon t follows normal with mean 0, standard deviation 1. This can be more general. Doesn't have to be restricted. There's all kinds of variations people have looked at. Okay. So just to give you an idea here, this is mainly modeling the square of the variance, square of the return as a function of its own past. Okay. So there are some limitations. I think it assumes that shocks are symmetric, and this practical issue, arch models tend to over predict. That means that if you see a lot of bouncing, it sort of tells you it's going to bounce around again, I think, which may or may not hold. Okay. So this is similar to autoregressive process, as I mentioned before. Okay. So I think there is a nice modification that's often used in practice. This is called generalized arch model. Okay. And this is similar to ARMA modeling. Okay. And let me show you the difference here. So if you look at this, the first part of the equation is the same, but the second equation you can see sigma t squared depends on its own variance in the own past. It also depends on zt minus I squared, the past zt values. So this process is known as Garch PQ. This is similar to ARMA PQ type of model. Okay. Again, let me show you how this works in terms of simple adjustments. Okay. So again, I will illustrate this with only Garch 1-1 model. Okay. I think some conditions that are not mentioned there, let me write it here. I think one of the conditions, alpha 0 should be positive, alpha j and beta j should be greater than or equal to 0, and important condition is that I ranging from 1 to maximum of p and q, alpha I plus beta I, the sum should be less than 1, sort of stationarity condition here. Okay. Okay. So let me show you the connection between Garch 1-1 and ARMA 1-1. Okay. We are going to do the same thing that I mentioned before. Here I think Garch 1-1 sigma t squared is given as alpha 0 plus beta 1 times zt, I think sigma t minus 1 squared plus alpha 1 z of t minus 1 squared. Okay. So we'll follow the same kind of manipulation that we did with the arch model. Write zt squared as sigma t squared plus zt squared minus sigma t squared. Okay. So sigma t squared is given as alpha 0 plus beta 1 sigma t minus 1 squared plus alpha 1 z of t minus 1 squared plus zt squared minus sigma t squared. Okay. So we'll do one more round of manipulation here. This is going to be alpha 0 plus alpha 1 plus beta 1 times zt minus 1 squared. Since I added beta 1, I have to take it out, and then that's done through minus beta 1 times zt minus 1 squared minus sigma t minus 1 squared plus zt squared minus sigma t squared. So this is same as writing alpha 0 plus alpha 1 plus beta 1 zt minus 1 squared, and then if I call this as a new t as the error term here, this is same as writing nu t minus beta times nu t minus 1. So you can see that zt squared depends upon its past zt minus 1 squared. These are like a moving average type of error term here. So from here, this form of this looks like zt squared follows ARMA 1-1. Okay. I think the main thing you need to worry about here is that stationarity condition. So what is the condition for stationarity? This coefficient should be less than 1, right? If it gets closer to 1, that means that again you have zt squared could be non-stationary. Alpha 1 plus beta 1 should be less than 1 for stationarity. Okay. So quick way to check whether there is any arch effect or not is to either you can take return square and go through autocorrelation function, right? If there is any autocorrelation function, that would automatically say that there is effect. There is a formal way to check. One formal way to check is that either you can, as I mentioned before, you can use the time series test for residuals. You can use this Jung box test to go through the calculation. So a simple test people recommend in practice is that take this RT squared, regress it on the past Q values and compute R squared, and if R squared is close to 0, which would confirm the fact that alpha 1 to alpha q is 0, that means that there is no dependence that you can cache in. Otherwise you can take that there is no volatility change over time. Okay, that's a simple way to do that. Okay, so before I get to it, let me ask any question on it. I'm going to show you an example, I think, that I posted on the coursework. I think I posted. If I have not posted, I'll post it right away. So this is a hope I posted it. Sorry, I have not done that. Sorry, I have not done it. I'll post it right away. A little after the class, I'll just go ahead and post it. Okay. So this is the data that I mentioned. This is a weekly exchange rate data. Okay, and it also gives you the R program that you can use. Okay, and and I go through the. So this is the distribution of the returns, and you can see that there is some observations away from the tails. So you can also check Jark-Bara test, and I think I have done it here somewhere. I'll show you where it is. I'll post it so you can take a look at it. Okay. Before we get too far, I think that is the plot of the exchange rates, and you can see that from the plot it's clear that it's non-stationary, right? And the autocorrelation function that I have on the right hand side sort of confirm that. You see that? And then this is the difference exchange rate, that is like return exchange rate, and you can see if you look at the autocorrelation function, is there any autocorrelation here? 0 is by default, it computes autocorrelation to be 1. That's how R is set up. But beyond that, is there any autocorrelation? There is no autocorrelation here. And this is the square data, return square. And when I compute the autocorrelation of this squared return, you can see there is some autocorrelations here. Can you see that? Okay. So that means that there is some dependence in RT squared which you can model. Okay. So there is some arch effect, and if I go down, I think somewhere here I have that. Okay. Remember we talked about so the next set of calculations here, what I do here is to lag them, essentially looking at that arch effect test. So I take RT squared, lag 1, lag 2, lag 4. So I went up to Q is equal to 4, and I wanted to check if there is any impact of this, and this gives you the regression calculations. And if I go down, I think all the calculations are automatically done here. You can see that lag 3 and 4 are significant, Z3 and Z4 are significant. Although R squared value is pretty small, R squared is 0.04, still I go through the test, you can see the p value is 0.00 7485. Okay. So that clearly indicates that there is some volatility clustering, and you can test for it. I think this is the test that I have here. Okay. And I think the key part of it is here. I think this is I also have the Jark-Bara test, also diagnostic test. But the key part of it is this equation that I fit. I fit a Garch model here, and you can see I'm fitting a Garch 1-1 model. Okay. How do I make this bigger? Can someone help? How do I myself don't have. Which one?
The bottom right one.
Here I see. Oh, okay. Is it better now? Okay. So you can see that I fit a Garch 1-1 model here, and these are the estimates that I get. It also does a diagnostic test, Jark-Bara test, going through this. But let me focus on this part here. What exactly is this model that we have? Okay. So this model says that so we are fitting this Garch 1-1 model. So essentially the model says that sigma hat t squared is equal to, I'll just write down the estimates here, 3.069 10 to the power minus 5. I think you see the numbers being small mainly because of returns are already small. I'm squaring them. So, and the next number is 0.066. Okay, that is alpha 1. So that's going to be 0.066 zt minus 1 square, and beta 1 is given as 0.89 sigma t minus 1 square. Okay. So that is a model you can use for predicting next period's prediction. Okay. So one key thing I want you to observe here is the following. If I add up these two numbers, what do I get? If I add up this alpha 1 and beta 1, what do I get? 0.95, which is almost 1. Okay. So which means that this process, this variance process is non-stationary. Okay. So this could be, so whenever you have non-stationary process, how do you deal with them? In the case of modeling the mean, what we did was to look at the difference between the successive observation. Same idea goes through here too. Okay. So if you want to model this one step further, I think you can look at what we call as integrated Garch models. Okay. What exactly are the integrated Garch model? They look at sigma t squared minus sigma t minus 1 squared and model this as a function of its past. Okay. Look at the difference between successive variances and go through the calculations. Okay. So there is a lot of work done in this area, but as far as I am concerned, I think I would like you to use this information, volatility forecasting, mainly in developing technical rules. As I mentioned, still the volatility models tend to be fairly not so good when it comes to prediction. Okay. So you need to really incorporate other type of information if you want to be successful. Okay. I'll post it so you can take a look at it. Okay, I think before I do that, I want to briefly show you. There's a lot of information here that we still have to cover. So before I go too far, I think I want to show you an example of high frequency data that I have posted. Hope I can open this without much problem because it's a fairly big file. So as it opens, we are able to download the data from Words on 2013 data. Do you have any of you have any questions? Any problem with that? Okay. I think you'll see that this is somewhat a simplified version of the model here. So this is the data for Microsoft, and data for Microsoft, and you can see that what is given here is the symbol and then the date and then the time of transaction, the price, the size. I know what the G27 car means, but there is also the last one gives you the exchange. Okay, so I looked at only the trade data, okay, which when the trade occurs. There is also other code data, right? How many people are posting on buy side, sell side, and all that information is given here too. Okay, the key here is that you can see lots of transactions occur at different points in time. Just to, when you do the analysis, try to restrict to the trading hours 9:30 to 4. Okay, but even when you do the restriction to 9:30 to 4, you will see that at the beginning around 9:30 there will be lots of transactions taking place, mainly because these are pending orders that get processed when the market opens. Okay, so usually I tend to omit the first 5 minutes and then start from there up to 4 p.m. Okay, the key part of it I want to keep in mind is that you can see the data comes at irregular time intervals here. In some cases you may see that there is at the same timestamp here, and this happens mainly because of latency issues. It gets recorded a little bit late, so it happens at the same time. So before I do any processing, I would tend to aggregate the data to those time units and then look at the duration. Duration is the time difference between successive observations. You can see it starts as 4:31, there is 19 seconds, and then you 3 seconds, then you 4 seconds, and so on. So studying how fast these transactions move during the course of the time has become the most useful topic in the recent years. Okay, the duration between successive transactions, how fast it happens, can provide some information about whether there is any information flow about that stock or not. Okay. So I posted this data. I would like you to familiarize yourself with that, because the homework you are doing is going to be somewhat similar to what I posted here. Okay, so I'm going to stop here, and I'll post that handout on the coursework. If you have any questions, come and send me a note. Okay, so there is a discussion forum in the coursework site. So if you have any questions on the assignment, please post it. Either myself or the TAs would answer the questions. Okay.